Everyone, welcome to my YouTube channel. So in this video I'm going to talk about the LLM training process. So we will basically talk about the different phases of training a LLM, and mainly we will focus about the RLHF part, which is reinforcement learning from human feedback, right? So this will be a multi-part series or multi-part videos where at first I will talk about the different phases of different training phases of LLM training, and then we will talk about what are the demerits of each of these phases and how we can overcome with the next phase that is lined up in this whole training process, right? So let's first talk about the different phases of LLM training, right? So the first phase is the pre-training phase, which we also call as language modeling, right? So in this phase we mainly train our LLM on a large scale of data set. That is a large data set we will use to train a model, and this large data set is on a scale of over 1 trillion tokens. So these tokens are nothing but, if we are thinking about a sentence, right? So each of the words can be one of the token. Now each of the words can be also split into multiple tokens, so that is a different concept, but just imagine that we are kind of training this model over 1 trillion tokens, and those tokens are mainly scrapped over the internet, right? So with this concept, what we will do is we will mainly optimize this model for text completion or the next token prediction task, right? So this model is not, now at this point this model is not ready for conversational task, right? So if you go and talk to this model will not give you the results which you desire for, right? So that is one of the drawback of this model, but what we get is we can treat this model as kind of a completion machine, which is like excels at the task of next word prediction or the next token predictions. So some of the examples are GPT series of model which comes from OpenAI, then there is Llama from Meta, and also the stable LM from the stability AI, right? So at this phase you can think this model as kind of a untamed dinosaur, right? Which is kind of a huge model which is trained on very large amount of tokens, which generally spans over 1 trillion tokens, and this model is kind of a very huge gigantic dinosaur which you can think of, and this model is not optimized for conversational purpose, right? So now the next phase is, or the second phase is supervised fine tuning, which we also call as SFT phase, supervised fine tuning phase, and we also call it as instruction fine tuning, right? So in this phase what we generally do is we use high quality data which is mainly focused for conversational AI purpose, right? So we train our train our language model with a high quality data set which will be better suited for the conversational AI, right? So, and this data set comes in a format which is like a prompt response format. So we have the prompt or the questions, and also the corresponding response. So this we generally call as demonstration data, right? So with this, the main goal for this phase of this LLM training or this SFT phase is to optimize the pre-trained model to generate responses that users are looking for, right? So you will train with this prompt and response pairs, which we also call as demonstration data, and then we assume that the model will excel at the conversational task. So if a user asks a question to this model, then the model will understand that context of the question, and it will give a better result while comparing with the first pre-training phase, right? So the goal is to optimize the pre-trained model to generate responses that users are looking for, right? So OpenAI kind of calls this SFT as behavior cloning. So what this behavior cloning is, you demonstrate how the model should behave and the model will clone that behavior, right? So we are kind of demonstrating that behavior using this prompt and response pair, and we expect the model to just clone that behavior so that it will excel in the conversational task, right? So some of the examples are Dolly V2 or the Falcon Instruct, and the demonstration data that we are using here that scales over 10,000 to 100,000 prompt response pairs, right? So the volume is kind of decreasing. Like we started with like a data set which spans across trillion token, and now we are kind of reducing that data set, and we are kind of passing a high quality data set to the model which scales like 10,000 to 100,000 prompt response pairs, and we are expecting that the model will excel at the conversational AI task, right? So now we can say that we started with a like untamed dinosaur. Now we are kind of get a grown-up child which can understand the user questions or the questions coming from different sources, and it will be able to answer those questions, right? So those answer may not be perfect, so that is kind of the drawback of this supervised fine-tuning process. So let's talk about so far like what we have gone through using this diagram, right? So this is from one of the famous blog from Chip. So what we start with a low quality data, and those are kind of scrapped from the internet. Then we kind of pass those data through a language model, and we kind of get a pre-trained LLM, right? So the scale is like greater than 1 trillion tokens, and the examples are like Falcon, GPT series of models, then Bloom, Stable LM. All these models are kind of pre-trained models. Then using that pre-trained model, what we will do is we will pass the demonstration data, which is kind of a prompt response pairs, and we fine-tune our model which will excel at the conversational task, right? So for pre-trained model, that is excel at completion task or the next word or next token prediction. But using this SFT training process, we will get a model which can also excel at like conversational AI stuff, right? And this data, which is like a high quality data that has that ranges from 10k to 100k, right? Prompt response pair. But after all this, you may not get the optimal results, right? So even after fine tuning process, the model can still perform poorly on several alignment criteria, right? So what are these alignment criteria are? So let's discuss about that. So helpfulness is one of the criteria. So you are kind of putting some questions and you are asking some sort of help, but the model may not give you your desired output, which is may not be helpful to your question or to your context which you are passing as a prompt, right? Then there are several other alignment criterias like harmfulness. So model may be giving certain responses which may be in terms of toxicity also it is kind of performing bad, and also it is kind of spitting out some harmful behaviors as a response. Then there is honesty. So model may not give you the response in an honest fashion, and the last but not the least, it can also hallucinate, right? It can make up like its own answers, and then it will give you that response as a prompt, right? So with all this, these are some of the general alignment criteria which is the SFT model still suffers, and using like bringing the human in the loop with the help of reinforcement learning with human feedback, we expect that model will kind of perform well on this type of task or this type of alignment criteria, right? So as we kind of started with reinforcement learning with human feedback, now first I wanted to take you through some of the basics of reinforcement learning. So this is kind of a refresher of reinforcement learning concepts. So first, reinforcement learning is kind of a subset of ML. So generally this reinforcement learning is a subset of ML which is different from the conventional supervised and unsupervised machine learning, right? So few of the characteristics of the reinforcement learning, like humans, the reinforcement learning algorithm also learns by interacting with the environment, right? These interactions are often sequential in nature, and the learning which happens, that is active learning rather than the passive learning. And the model can also learn without seeing the optimal examples. So with its own intelligence, if you don't provide also the optimal examples, it can still learn that without seeing optimal examples, right? And this algorithm is generally goal oriented algorithms which aims to maximize the long term rewards, right? So the main aim of this algorithm is to find the long-term rewards, right? Now a typical reinforcement learning example, right? So after exam childhood days, right? So I hope you remember that. So when we used to get like good marks in the exam, we used to get candy from our parents or from teacher. We used to get some positive reward, right? But if we are performing bad, then a stick or some other treatments for the bad result, right? So this is a typical set of reinforcement learning problem. I hope you got an understanding of how the basic of reinforcement learning works. Now let's talk about how reinforcement learning is different in while compared with the machine learning, right? So first of all, the aim is to choose the optimal task in case of reinforcement learning, or choose the optimal action. What this action and what the terminologies which I am using, that I will talk about in very much in detail in the next few minutes. But for the aim of a machine learning task is to predict, classify, or grouping is nothing but the clustering, right? So then there is uncertainty over the environment, right? So but in case of machine learning, the data set which we are passing to the model, which is X, that is fully known. So environment is fully known for the machine learning. But in case of reinforcement learning, your X is not fully known, so you do not know the environment fully. So you learn by interacting with the environment. Then it learns by exploring the environment in case of reinforcement learning, and for machine learning it learns by finding the patterns that are available in the data. The training process is the training process outcome for reinforcement learning is the optimal policy, and for machine learning the training process outcome is the best model, right? Then there are dependency in the previous action that the reinforcement learning model has taken. But in case of machine learning, each observation is kind of independent in nature, right? Okay, now let's talk about the few of the terminologies. First of all, like the agent. So agent is kind of the algorithm which we are trying to build. Then the agent takes certain actions, the set of possible actions the agent can take, that we call as action. And agent interacts with the environment, so environment receives an action and produces a new observation and reward. So that reward is kind of an indication how the agent is doing at a particular timestamp, right? So this reward is generally a scalar feedback, that you should remember, that the reward is kind of a scalar feedback, because this concept we will use when we talk about the RLHF, right? So it's not only the environment kind of emits the reward, it also emits a new state. So based on the action, the agent will move to a different state, and that state is kind of a representation of the agent in the environment, right? So using the state representation, the RL algorithm picks the next best action, right? Talk about a few two different concepts which is very much required for understanding the RLHF process. So first of all is like, what is expected value or the reward, right? So the weighted sum of each possible outcome is kind of a reward. So if you are in a stochastic environment, right, so your action, like if there are two paths, right, and your action kind of depends on has a separate probabilities, right? So being on a state S, there is a 60% chance that you go to a different next state, and also you kind of have a another 40% probability of going to a different state where the reward is kind of 0, which is associated with 0.4 probability, and also we have a reward which is associated, reward equals to 1, which is associated with 0.6. Now the cumulative reward, which being at state S the agent might get, is kind of the, you have to multiply each of the probability with the reward value, then sum, and then you will get the total reward or the expected value, right? So for this example, if you multiply 0.6 with 1, you will get 0.6, and then you multiply with 0.4 with 0, you will get 0. So the expected value or the reward for being state is equals to 0.6, right? Then we have this concept of value function, which tells you how good is any given state for an agent, right? So for a deterministic world where there is no randomness in the environment, so the action you are desired to take, you will always able to take that action. That is kind of a deterministic world, right? So the value of a state is just the sum of all the future rewards, right? So if I take this example, like the agent is at the first step, then it will like traverse through different paths of the this maze, and it will finally end in a final state, right? So being at state 1, which is S1, the value function is kind of the sum of all the future rewards, right? So if you like visualize this process as the future rewards are like R2, R3, R4 plus till it will go to the last reward, which is Rn, right? So that is kind of which tells you the value function for being at state S1, right? So if you just simplify this equation, right, so now we can write down vs2 is nothing but r3, which starts from r3 because we will only sum the future rewards, right? So from r3 it will go till rn, right? So that is a representation of vs2. Now we can plug this vs2 in the first equation, and we can get the vs1 is nothing but r2 plus vs2, right? So now there are certain uncertainties in the environment, right? So your future rewards is not very easy to predict, right? So we kind of implement we can bring in a multiplying factor, which is a discounting factor, and as there are uncertainties in the future reward, so because it's always harder to predict the future rather than the next few rewards which are very soon to happen, right? So we can bring in this discount factor and we can represent the value function like this, right? And for stochastic behavior, which we use as Bellman equation, so here we kind of straight away we cannot sum all the future rewards, so we need to take the expected value of the future rewards, right? So which I already talked about at the starting of this slide, right? So this vs is nothing but the expectation of r plus discount factor multiplied by vs dash, right? So this s dash is nothing but the next state, and r is the reward from going from s to s dash, right? So you are starting from a state which is s, and the next state is s dash, right? So that is kind of the expected value for stochastic behavior, right? Of this reinforcement learning refresher part, so we will talk about what is policies, right? So policy is kind of a function that maps a given state to action, right? So that action can be deterministic in nature, so you always get to perform the action you desired for. But if there are certain uncertainties in the environment, so then we kind of bring in the probability of actions, right? So if you just take an example of an agent is kind of moving in a maze, right? So if that maze is not slippery, then that is kind of a deterministic action. So if the agent is trying to go in a forward direction, it will always end up in the forward direction path, right? But if that maze is kind of a slippery and there is no certainty that if the agent wants to move forward, it will always end up in the forward direction. It can move into a different direction due to the stochastic nature of the environment, right? So if an agent follows a policy pi at a time t, then pi of a given s means that at time t under the policy pi, which is the agent is kind of following a certain policy, right? So the probability of taking an action is probability of taking action a in state s is pi a given s, right? So this is how you can denote a policy. So policy is nothing but which maps action on a given state, right? So for deterministic policy is a equals to pi s, but in case of stochastic environment, so you will come up with a stochastic policy which is nothing but pi of a given s, right? So which is nothing but probability of taking action equals to a being in the state equals to s. This is what I was trying to explain. Like if you are in a state b and if there are a stochasticity in the environment, so if you want to move to a particular direction, it may not happen that you will always end up in that desired location, right? So there are probabilities associated like going left, right, and also there is a probability associated being in the same state, right? So this is kind of a representation of the stochastic policy, and where the probabilities are associated for each of the action. And for stochastic policy, you need to use the probability as one of the parameters, right? So all of this reinforcement learning thing which we are talking about, the main aim or objective is to find the optimal policy, right? So what this optimal policy is, a policy that is better than or at least same as all other policies, is called optimal policy, right? So if we have two policies, right, pi1 and pi2, now we have two states, right, s1 and s2, and we also know the what are the value functions for each of these states for different policies, like for the policy 1 and policy 2. So here you can see like the policy 1 is kind of better performing while compared to the policy 2. So in the S1 state, both the policies is kind of giving you the same value function, but for S2, your policy 1 is kind of giving you better rewards or the better value function, right? So with this criteria, we can say that pi 1 is kind of greater than or equals to of pi 2, right? So if you want to pick a policy for this particular environment, more or less we will always pick the pi 1, right? So with this, I will try to end this video. This is already a long video, so in the next video I will talk about depth analysis of reinforcement learning human feedback and how that kind of fits into the concept of LLM training phase. And I hope you got a good understanding of reinforcement learning and also the first two step of LLM training phase. With this, I will end this video. If you have any questions, please comment, and if you haven't subscribed this channel, please subscribe, like and share with your friends. Thank you. See you in the next video.